Hello and welcome to, what is this, my fifth video? Something like that. This is Mikrotik routing. And so not only is it Mikrotik routing, but it's also kind of the fundamentals behind routing itself. You got to kind of put yourself in the perspective of the router, you know. Because really routing, that's what it is. It's the viewpoint of one router, you know. He's your typical 3-year-old child. He's the center of the universe. He doesn't really care about anybody else. It's all me, me, me. So let's go ahead and get started. Topics to kind of cover are going to be static routing and then your dynamic routing protocols like your RISP, which I'm going to talk about briefly. I'm going to go ahead and tell you right off the bat that I'm not going to recommend you use it. It was the very first routing protocol out there, and it's not really used anymore. I would really say only use it if you absolutely must. It's somewhat inefficient. Anyways, we'll get to that. Then your OSPF and then your BGP. So what is routing? Wikipedia is usually who I go to for these explanations, and they've got a good lengthy explanation in the context of the class. Really, it's going to be when I'm the router, because we're pretending we're the router right now, it's which path should I take to get to a specific destination. So I've got a packet and I need to send it somewhere. Where do I send it? That's what routing is. And so what is a routing table? Every device that does TCP/IP and transfers information on the internet actually has a routing table, whether you know it's there or not. Even your Windows machine here, if you do route print, you'll see that your Windows machine actually has a route table itself, and you can do routing. Like Windows XP, you can edit a registry setting and you can actually route through the guy, and you can manually add routes. Just so you know. I didn't know that for I don't know, a couple of years, few years when I was working with computers. So I thought that was kind of cool. Routing tables a list of networks. Next, hop information to reach those networks. Router cares only about itself and how to get to its directly connected neighbors. So when a router wants to send a packet, does it care that you actually live 6 hops down the road? You know, 6 different routers. And whenever I'm talking about a connection between a router, I call it a hop a lot of times. It's common nomenclature. So a hop is going to be you know, a direct connection between you and another router. Do I care that you're 6 routers down, 6 hops down? No, I don't. I only care that you're kind of that direction, so I'm going to throw it to my directly connected neighbor. And like I said earlier, that routes can be added to that routing table either statically or dynamically with a routing protocol. There is a difference between routed protocols and routing protocols. A routed protocol is going to be like TCP/IP, IPX, whereas a routing protocol is going to be something that's dynamic, like your OSPF or your RIP, something that dynamically builds this routing table. Hot potato routing. I don't know about anywhere else but here in the States, and maybe it's just a southern thing, I don't know. We had this game called Hot Potato we played when we were little kids. The idea is there's an object that everybody generally stands in a circle, and it's called the hot potato, and you're only supposed to have it for a short amount of time because in theory it's a hot potato, so you just throw it around back and forth. As soon as you get it, you throw it to the next kid, you know, and it's theoretically hot, you know, so it burns you, so you don't want to hold it long. Well, if you imagine playing hot potato as a child, only instead of being in a ring, you're in a straight line. Pretend you're in a straight line. You're in the center of this line. You've got nothing but boys to you on your left and nothing but girls to you on the right. So as the potato is making it, you know, down the line, you don't care from whence it came. It's just when it arrives to you, you say, who's this destined for? Is it supposed to go to the girls or to the boys? So you look at your route table. That's your routing table. You've got boys left, girls right. That's your routing table. That's all you've got. That's as specific as it is. And you know, if it's destined for the boys, you know what? You throw it to Jimmy, the kid that's right next to you on the left. That boy, you throw it right to him, right? You don't care if it's destined for Tom, that's right after Jimmy, or Bob, that's third in line. You don't care. You just know that boys left, so you throw it to the boys, and then you're done with it. Same thing with the girls. Girls right. As soon as it comes to you, oh, it's got a destination of the girls, so I just throw it over there. And And you don't care. Again, you don't care how far down the chain these people are because you've got nothing more specific than boys, girls. And in your routing table, you can actually build it so that it's so specific that you know every single person in there. You know, every boy to your left and you know how far away he is. You can actually have every single boy in there and say every boy, you know, that Bob left, Tom left, or you can just say boys as a whole. And that's the difference between kind of doing like a network as opposed to individual host addresses. So the boys are a network, and so that's as specific as we have it. So send it to the left, girls to the right. Let's see, what else do we have? Oh, yeah. There's also a lot of times something known as a default gateway or gateway of last resort, in that if I get a destination that I'm unaware of, you know, that I don't have a specific route that matches in my table for that network or that host, then I'll send it to my gateway of last resort. And the example I used in the slide is a kid named Pat, you know, which can be a boy or a girl. So in this situation, if I've got a gateway of last resort for Pat, say it's to the left, then I'll just throw that direction. Now, if I don't have a gateway of last resort, and I don't have a network statement that matches that, or an individual host address, nothing very specific at all, and no default gateway, I'm just going to throw that in the trash, throw it in the bit bucket, and that's what a router does. If you don't have a default gateway, and in your route table there's no network or host that's going to encompass that destination address, you just throw it away. So, moving on to actually viewing the route table on a device. I showed you how to do it on a Windows machine. How you do it on a Mikrotik, you got IP routes. That's one of the basic things. And so on router 1 here, you see I've got one static route right there. I've got actually 2. This one's disabled. That one's going to be used later. Here's dynamic routes. Anytime I create an IP address, excuse me, on the router, it'll automatically create a route for that. You know, it'll throw something in the route table. IP addresses. You see I have all these addresses assigned to the router, and then it's automatically, that's what the D stands for, dynamic, right there. And A is for active, C is for connected. Up here the S is for static. And so you can see X is going to be for disabled. So you can see everything in the route table. If we scroll to the right a little bit, you can see there next hop reachable device. So let's see, or rather there, I think that's the local address for them. That's the route table. Static routing. So adding routes into the router manually, you know, by the route command in their IP route, it's called static routing. We've already talked about that. That's where you actually manually put every single route in. A case for static routing. If you have a linear network, it's in a straight line, or it's a very small network, that's a good use for static routing. Almost all default routes are static routes unless you're like pulling your default from BGP or something like that. It can always be injected by somebody else's domain, but generally your default route's static. Yeah, small networks, static is a good option because there's no overhead incurred. You know, when you're running a dynamic routing protocol, then the CPU actually has to keep track of all that stuff. It incurs additional memory hits because you're holding, you know, LSA tables, you know, tables for OSPF that contain all of your routes, or BGP, you know, the BGP internet, you know, the full internet route table is looking somewhere around 300,000 routes, and that takes a memory footprint. Plus, whenever these guys calculate their algorithms to find best path and all that good stuff, or reconvergence, it consumes CPU cycles. Static routes don't consume CPU cycles. You know, it's something you manually put in there that never changes. So the router actually doesn't have to work for it. You know, all it does is just look at its table and go. And they're also relatively straightforward. You know, as the network gets bigger, it gets more complicated, more complex. But you can actually do summarization. So if you large chunks of subnets that can easily be summarized, you don't technically need a dynamic routing protocol at that point. So looking at some of the options here, and I kind of go over a few of the options for adding a route. You got your destination address, so whatever host or subnet you want to get to, you put right here. Gateway is going to be your next hop router. If you've got a dynamically assigned interface like a PPPoE interface, you can hit the drop down and choose that interface. Let me scoot this guy over a little bit. There we go. Check gateway. This will actually allow you to ping the gateway to make sure it's up. That's not always going to be an effective option. Say you have a T1 coming in, so you've got a specialized router that terminates the T1. Well, say that router's up, and that's fine, but say the T1 interface actually goes down. This check gateway is not going to do you much good because it's only going to check your directly connected neighbor. Distance. This is something I talk about, I think, in this slide. Yeah, so I'll go ahead and cover it. Distance, also known in Cisco as administrative distance, is a route's priority in the routing table. There can be multiple routes to the same place. There can be multiple identical routes, but if they have different distances, whichever one has the lowest distance will win, and that one will actually get put into the route table. So by default, a static route's got a distance of 1. You can actually change it to whatever you want it to be. Right there. eBGP, external BGP routes learned from a neighbor, is 20. OSPF defaults to 110. iBGP defaults to 200. There's other, say, Cisco routing protocols like EIGRP, which is going to be 90. The old legacy IGRP, which is going to be 100. And then you've got ISIS in Cisco, which is going to be 115. So anyway, if you pull an eBGP route and then you've got the exact same route known via OSPF, it's going to take the eBGP route because its administrative distance is going to be 20, which is lower. There we go, better. Static routes default to 1, so they're almost always used, although you can elevate that administrative distance to allow other things to take precedence. Moving on. Default gateway. Yeah, we talked a little bit about the default gateway and the hot potato route thing. That's just going to be, if I don't know what else to do with this route, send it this direction, which is generally what you do right at your board router. You'll say, because most people only have a single ISP, you'll say, to get to the internet, every unknown host out there, go ahead and do a destination of 0000/0 and send it to whatever the IP address is of my next hop. And so we've got a static routing example right here. So what I'm going to do is I'm going to adjust this so you can't, or rather so we can see this big. Okay, I'm doing this 4 routers deep. So Mikrotik 1, which I was doing my examples on there, you can see I have a static route as per the diagram here. Here's Mikrotik 1, Ethernet 1 interface. He's got 1.1.1 assigned. I've already put the IP addresses on here because there's a lot of IPs on here just to save us a little time. So his, since that's a /30, there's only 4 usable, there's 4 addresses in there. One's the network, one's the broadcast, which immediately eliminates 2, so we've only got 2 available addresses, which mean the very next hop over here, my provider's IP is going to be 1.1.1.2. So if you look at this guy, you see default route 0000/0, gateway 1.1.1.2. So we've got our static in there. And then what am I going to do to get back to these other networks? Because we'll say that what I want to do is I want to ping this 192.168.4.1 interface. That's my ultimate goal. I want Mikrotik 1 to be able to ping that IP. And so what a lot of people think of as when people are troubleshooting routing problems or are setting up a little bit of static routing or adding a new subnet, people often think, well, okay, Mikrotik 1, I want to get him to ping 192.168.4.1. So what they'll do is they'll put in the route on 1, and then they'll move to 2, and they'll put in the route, to get to 192.168.4.1, that subnet 4.0/24. They'll put it in here, and they'll put it in 3, and then once it gets to 4, they're done. They think that's complete, and so 1 knows how to get to that subnet all the way over there, and then they can't figure out why it doesn't work. Well, fundamentally, you always have to remember a router needs to know how to get to a destination, but then when the traffic hits and needs to return, routers entirely in the chain also need to know how to get back. So you have to remember to put over here on 3, not only does he have to know how to get to 192.168.4.0, but he also needs to know how to get back to 10.0.1.1. So it's you have to complete the chain. You have to go all the way and return all the way. So what we're going to do is Mikrotik 1. Let me see. So as you can see in here, we use the majority of our routing is 10.0.x.x. So what we're going to do is we're going to say anything, really anything 10 dot is this way. That's how we're going to do it. I know up here in my example I've got a /22. What is that going to be? 16, 17, 18, 19, 20, 21, 22. That's 6, 128. So we're just going to say, we'll just say anything 10 explicitly, because I'm lazy. So I'll add a static route. I'm going to say 0.0.0/8. Anything 10, go to my next hop, so this router, his next hop is 10.0.1.2. 10.0.1.2. Okay. So this guy right now knows how to get to the 10 addressing, but he doesn't know how to get to the 192. So let's go ahead and add that. So we'll just say 192.168. 0.0/21. That's going to encompass all the ranges we're using right now. And we'll have the same gateway, which was 10.0.1.2. Okay. Now we're going to go to Mikrotik 2 real quick, because he's the next link in the chain, and I like to just kind of work my way across. And so what we're going to do is first we're going to put the default route, since the internet's this way, which means if I don't know anything else about it, send it that way. So I'm going to say IP routes. I'm going to go ahead and add a default route to 10.0.1.1 was his IP address. Let me scoot this over a little bit. Okay, so we should be able to go ahead and go in Mikrotik 1. We're going to go to Tools, Ping. We're going to ping 192.168.2.1. That's the IP address bound to this Ether3. Since we put in a route for 10 and 192, it should head this way. We put in a default route so it knows how to get back. Not only does it know how to get back, but it's whenever you're just doing a regular ping command, it's going to be source IP'd from whatever interface it's leaving. So it's leaving from 10.0.1.1, and I made all these /24s just so we wouldn't have to worry about subnetting. But whenever it leaves this, whatever interface it leaves, it's going to be sourced from that IP address. This guy's already got this subnet assigned to that interface, so he's automatically going to know how to get back there. But theoretically, this guy wouldn't know how to get to that that 2.1 without that route we put in there. Alright, so we got our first Link in the chain done. So now let's go to Mikrotik 3. We got this guy right here. We need to actually finish off Mikrotik 2's config real quick. So looking at this guy, we've got, and for loopbacks, in Cisco, loopback is a virtual interface you configure that really just holds an IP address for you. Usually you're going to use that to assign a IP address for like a router ID for OSPF if you want it to actually be reachable via that, or IBGP. Usually you peer via the loopback interface. That way, if one of your internal local interfaces go down, it'll still reroute and be able to peer with that loopback IP. So throughout the rest of this, the OSPF and the BGP example, we're going to be using a loopback. So I've got the loopbacks in here, and they're just host IPs /32s, which means a single IP address. So this guy needs to know how to get to default, which we already put in there. So everything in this direction he doesn't care about. He's going to send it that way. The only 10 dot that lives over here that he's not going to know about is, because what I'm going to do is I'm going to put a 10.0.0/8 going this way, which will encompass everything over there, and I'm going to put a single static route for 10.0.0.1. As you can see, there's a lot more 10 addressing over here than there is right here, and I can put a 10.0.0 10.0.0/8 address route going this way, even though 10.0.1.1 is right here, and he'll still be able to reach this even though his route table tells him to go that way, because he's got a directly connected subnet right there that encompasses that IP on this Mikrotik 1. So since it's a directly connected subnet, IP address assigned to the interface, he's already going to have a route in his route table. Remember, anytime you assign an IP, so that's just a more specific route in the route table. So you can have a less specific one pointing in opposite direction. As long as you have a more specific route pointing another direction, it'll take that. So in this Mikrotik 2, I'm going to say 10.0.0.0/8. Go to the right, which is 10.0.2.2. In Mikrotik 2, I'm also going to say any 192.168 lives this direction. What was that IP again? 10.0.2.2. And then we're going to add a single host route, 10.0.0.1, for that loopback on Mikrotik 1. This can be 10.0.1.1. Alright, so Mikrotik 2's route table is complete. Mikrotik 3. Go ahead and add his default gateway, which is going to be to the left. You always want that to point towards the internet. 10.0.2.1. Alright. So now that we have a default route, let's go ahead and try and ping 10.0.3.1, which is assigned to this interface right here from Mikrotik 1. So we've got the routing set up in place here. So it should hit here and then default route back over. 10.0.3.1. Alright. So I got my default route in. Now, look at Mikrotik 3. The only 10 addressing left over here is his directly connected interface, which we don't have to worry about. It's already in the route table. The only other remaining is this loopback IP right here in the 10 subnet. So I'll put a single static there, and our default route will go ahead and catch all of the 0, or rather 10-0 stuff this direction, so we don't have to add any extra 10 stuff. Also, I'm not going to put any 192 large encompassing subnet stuff in here because default will catch him. I'll just put a single static for this 192.168 right here. So really what you do is you just try and figure out the least amount of routes you can add to encompass the most stuff. So it's going to be 192.168.4.0/24. Next hop for this guy is 10.0.3.2. You can see right there, 10.0.3.2 is that Ethernet interface. That's why he's our next hop. I need to go ahead and put in his loopback as well, which was 10.0.0.4. That single host is also going to be available via 10.0.3.2. Okay. So that should be all of his routing table right there. Let's go ahead and add Mikrotik 4 in the mix, and since he's a stub over there on the end, he's only got one way to go anyway, so all we need is the single default route. Let's go ahead and add default route as being back to 10.0.3.1. Again, his next hop reachable router, 10.0.3.1 right there. That's his next hop router. So again, if we look at, and I've got the route tables right up here at the top, so that's 1, 2, 3, and 4. If you look at Mikrotik 1, he doesn't care that 192.168.4.1 lives on Mikrotik 4, or he also doesn't care that 192.168.2.1 lives on Mikrotik 2. As you can see here, all he knows is that anything that starts with 192.168 goes this direction, and that's all he cares about. It's actually not, that would be, anything 192.168 would be /16. So we've actually got it narrowed down to encompass really just a handful of addresses. What is that going to be? 128, 64, 32, 16, 8. So it would be 192.168.0 to 7.255, which is going to cover all of our subnets here. So anything that falls within that large scope of addresses go this way, right? He doesn't care that that specific individual host is here. He just knows the large subnet goes this way. So a route table isn't necessarily every single host's IP. It's going to be as large a subnet as it takes generally to cover all that. So rather, in lieu of putting all of these /24s in here to the right, I put in just 2 routes that would cover them all. Otherwise it would have taken let's see, 1 for that host. It'd be 1, 2, 3 for those host addresses, 4, 5, 6, 7. So 7 routes got culled down into 2 individual routes. So all of our routes should be in place, so we should be able to ping our ultimate goal 192.168.4.1, and there we have it. It's going from 1, making the hop all the way across. Now remember, every single hop, that individual router stops, looks at his route table, and says, 10.0.1.1 wants to send a ping to 192.168.4.1. So he looks in his route table and he says, go to this next hop right here, 10.0.1.2. He makes it to that hop. This router then stops, looks at his route table. I need to go to, he doesn't care about the source at this point. He says, I need to go to 192.168.4.1, looks at his route table. Next hop, 10.0.2.2. Heads that way again, 192.4.0. 10032. This router then looks at the route, sees that it's destined for one of his local interfaces, goes into the input chain, hits him, he responds, goes into the output chain, and it's returning back to its source. So it's going to head back to 10.0.1.1. Looks in his route table, he's got a default route, nothing more specific, so he hands it to that next hop for the default route, 10.0.3.1. Hits Mikrotik 3, does the same thing, looks at his default route. I need to go to 10.0.1.1, nothing more specific. Hits his default, makes it this way. Again, it would technically hit his default, only he's got a directly connected subnet, which is going to appear to be a more specific route, so he'll take that, which is going to pop him out this interface and ultimately completes the chain. And I know I spent a lot of time on this, but static routing really teaches you the fundamental of routing. Nothing teaches you better. I mean, generally you can turn on OSPF with all its defaults and your routes will come up and everything will just work. But by doing a somewhat complicated configuration via OSPF in the lab at least once will really help to teach you how routing works fundamentally, and also help you troubleshoot. You know, a good situation, or rather a good test for this kind of thing is to configure your network, get it working, you know, get a sense of accomplishment, and then have somebody come in there and break something without you knowing it. In your lab, of course, never in the field. And then go back through and try and troubleshoot. You know, walk through your steps to figure out where it is that it broke down. You know, you'll ultimately learn a lot. So let's go ahead and continue. Before I continue, I'm going to kill all of those static routes. I'll just go ahead and delete them all together. I'm going to go ahead and leave that default route in there, but I'm going to ixnay this one. And I'm going to get rid of that 10 dot. Alright. Alright, so we've got a good base configuration here. Moving on. Floating static route. This is an interesting one. Generally, floating static routes are used for backup. Floating static routes really a Cisco set of nomenclature. It's where you have two routes going to the same destination. So you got, say, two defaults. So say I wanted to make this I think it's 10.0.1.2, I think, is the IP address of Mikrotik 2. And so a floating static route, one you would change the distance on to be your backup. So what happens is this route is installed. As you see, it's active, which means it's actively in use in the router, and the other ones just labeled as static. It's inactive right now. And so what that means is, since this one's got a distance of 1, it's going to be the active one. This one's got a distance of 10, so its distance is worse, so it won't be used, even though they're equal paths. So what happens is this one's used right here, this main one's used until, say, this interface goes down or for some reason this becomes unreachable. Either the interface does go down, or you're using check gateway right here and you have it set to ping and then it stops responding to ICMP. Well, then this route will automatically disable, and then as you saw, this other one will kick on, so it gives you kind of a backup scenario, and as soon as this one comes back online, the other one disables itself. So it'll go out the one interface, and then if that one fails for some reason, the other one will pick up where it left off. There's also something called equal cost load sharing, or equal cost destination, and that would be, if you hit that drop down arrow right there, you can add another destination for the same route, and this will kind of load balance, so it'll send to one, then it'll send the other. Say you wanted the route to live like that, you could have it kind of load balance between the two. Rather, should be 2 for that next hop. So load balance, and say this is beyond the scope of this, but just for the sake of interest, say you wanted twice the amount of traffic to go out the 1.1.1.2, Ethernet 1 interface as you did the Ether 2 interface. You can actually drop down and add 1.1.1.2 again in there, so it'll go to Ether 2, and then it'll service Ether 1, Ether 1, Ether 2, Ether 1, Ether 1. Like I said, that's beyond the scope of this, but I thought it would be something interesting for you guys to look at. So I'm going to go ahead and dump that now that we've talked about that. Moving on, RIP. So now we're getting into our dynamic routing protocols. RIP was the very first one created. Cat, go over here. Uses UDP 520. And most of this most of this information, the deep down information I'm going to tell you about these routing protocols, you don't really need to know them to operate, but really part of anybody's education is trying to get a fundamental understanding of how it really works. Because it can aid you sometimes to really deep down know how these things work. The metrics for this guy, since it is a distance vector protocol, is hop count. 15 hops is maximum. Once it hits 16, it's considered unreachable and no good. So you can only have a network that's 15 routers deep. Past that, it's going to be considered ineligible, and the route will be tossed in the trash. Uses no hello interval. Some of the routes will actually have a timed interval set where they'll just send hellos, and then when they need to, they'll send updates. This routing protocol actually sends all updates every routing interval, or rather every 30-second interval, because it just has an update interval. It doesn't actually have a hello interval. So you can see how that can be inefficient. Version 1 actually sent to a broadcast address you see right here, which means if you've got one big L2 network and you send a broadcast that goes out to every single port of every single switch, and so it can get really noisy. It can waste a lot of bandwidth. Back in the day when they only had 10 base T, that can be a big problem, especially if you're at half duplex somewhere. It's going to have a lot of standoffs there. RIP version 2 upgraded to use multicast. As you can see, here's the multicast address that it sends to. So a device has to register with the switch to say, hey, I want to listen on this multicast group. So it does make it a little bit more inefficient, or rather, it makes it a little bit more efficient. Triggered updates whenever routes change, but then again, every 30 seconds, it's sending every single route it's got anyway. Install 1 to 6 equal cost metric routes, defaults 4, which is like if it's got exact same route, like that default route we showed where it had multiples of the same default route, it'll actually install multiple of those in the routing table at once. Allows plain text or MD5 authentication. RIP version 2 actually allows variable link subnet masking or discontiguous networks to work. Before that, you couldn't have on one side of your network, you couldn't have 10.1 and then on the other side have 10.2 with a RIP router in between. Because those are discontiguous, it only it only respected the classful boundaries. So 10.0.0.0/8, it was absolute. It can only live on one interface or the other. Whereas RIP version 2 kind of got around that. Let's see, convergence can take up to 4 minutes in a moderately sized network, which is pretty insane. Convergence is when all routes are equal on all devices. Last point, don't use RIP unless you must. OSPF. This is my IGP of choice because it's very robust and it's open standards based. EIGRP, the Cisco proprietary one, is a fine protocol, but it's proprietary, and so nobody runs EIGRP but Cisco, which I don't care for. You know, I don't like being locked into anything, honestly. OSPF is really robust. There's a lot of extensions onto it. You know, a lot of great modifications. Let's see. Let's go ahead and talk about the fundamentals. It's a link state protocol. Refers to the fact that the topology information includes information about each data link along each link's current operational state. So what does that mean? That means OSPF inside of an area, it's got this concept of areas. So inside of an area, every router has the exact same link state database. It's a database of information on that area. You know, so it's going to have all the interfaces that are associated with that area, and all the routes that are associated with that area. The networks are going to be identical in every single router. So what this does is it allows each router to build a picture of the entire network and know how best to route through that network. So it doesn't just base things off of hop count. You know, it actually knows what every other router knows inside of that area in that process. All the topological information makes up the LSDB link state database. We just talked about that. It uses the Dijkstra algorithm to calculate each route. It's called the SPF calculation, shortest path first. And once a router becomes adjacent with another, and it pulls, you know, and both LSDBs are equal, it'll go ahead and run the SPF calculation, the Dijkstra algorithm, to figure out which paths are actually best to which networks, and then it'll install those in the routing table. It does support variable length subnet mask CIDR and discontinuous networks, and you get to it via routing OSPF. So one of the first things to do in OSPF is the process determines what its router ID is going to be. I've always set my router IDs manually. It's a best practice, and that's why I use loopbacks, so that I can also, because I also like the router ID, you know, or that loopback ID to be reachable throughout the network. It makes it easier to think of, you know, like backbone router 1 as being 10.0.0.1 and backbone router 2 being 10.0.0.2, as well as that being the router ID of the OSPF process, you know. So if I'm looking at the OSPF process, you know, on say router 4, when there's 10 routers in this same little area, and I see that a route was sourced from 10.0.0.1, well, I know that's backbone 1, as opposed to some arbitrary /30 IP address, you know, that happened to be assigned to that router. So it really makes it easier to tell. You know, only when you're going back and troubleshooting really does it become useful to be able to tell which router sourced what updates. If you don't manually set it, it'll use the lowest IP address configured on an active interface. Cisco uses the highest IP address starting on a loopback interface, and then using any up Ethernet interface, or, you know, any interface actually, really. Like I said, I suggest manually setting it, and we'll do that on router 1. Routing OSPF. You do that via the instance. And so I know Mikrotik 1 is 10.0.0.1. See, router ID set. And you can look at my IP addresses. You see 10.0.0.1 is configured on bridge 10. So what I just did was, well, rather what I originally did was went to bridge, created an interface, just a quick bridge interface, named it bridge 10. Didn't actually assign any ports to it. and then I went to IP addresses and just assigned whatever I wanted the loopback IP address to be, which is 10.0.0.1. So that's our router ID. OSPF messages. Excuse me. OSPF uses the hello message to discover neighbors, bring neighbor relationships to a two-way state, and check neighbor status. So it's sent out every few seconds. I believe it's every 10 seconds, I want to say, is the hello message in OSPF. And then you've got DBDs or DDs, database descriptors. Exchange light versions of each LSA on initial topology exchange helps determine which LSA the router should request to its neighbors. So what happens is the routers, once they exchange hellos, they become to a two-way state. Let's see. Yeah. I'll get a little bit more in depth in kind of each one of these and give you the flow in just a minute. But it's whenever they're first getting ready to exchange, they'll send these database descriptors, which have like small descriptions of the topology information, with which the receiving router can check his LSDB and say, oh, I need that route, and so then later he'll send this LSU, or rather he'll sing LSR linked state request that says, hey, I need the full routing information for these subnets that you sent me in that database descriptor. And so then he'll send back the LSU to the original requesting guy saying, here are the updates, and it gives you the full stuff. Link state ACK confirms receipt of LSU. LSAs are not OSPF messages, rather they are inside LSU messages to exchange information. So don't get confused on that. OSPF neighbors. When a link comes up, routers exchange hellos. They are in a two-way state. Hellos are sent to the all OSPF routers, which is 0.0.5. There's also all DR routers, which we'll talk about a little bit, which is 0.0.6. So OSPF does operate in multicast, so it's inherently more efficient than, say, something using broadcasts like GRIP version 1. Once hellos are exchanged, the following parameter checks are made. For neighbors to become adjacent, or rather for neighbors to even make it to the two-way state, they have to pass these steps. So if you have authentication set, it needs to be equal on both sides. If you have, in Cisco especially, there's a concept of a secondary IP, not so much in Mikrotik. You can just bind a bajillion IPs on Mikrotik and they all appear to be the same. But in Cisco, if you want to have additional IPs, you call them secondary IPs. Well, in Cisco, you have to have that OSPF process actually initiate on the primary subnet. So what does that mean? If you have 192.168.0.1 on an interface, as well as 10.0.0.1 on an interface, on your Mikrotik, and then on your Cisco side, you have 192.168.2 as the primary, and 10.0.0.0.2 as the secondary on the Cisco. So if you get rid of that 192 and you try and bring up OSPF with that secondary interface, or that secondary IP on the Cisco, it's not going to work. It has to always be in that primary subnet. So it has to have the same OSPF area, which we'll talk about the concept of areas in just a second. Same area type, which we'll talk about those concepts in a minute, which would be like stubby or not so stubby. You can't have duplicate router IDs. Each one has to be individual. Hello and dead timers must match, and I believe we're gonna. No, I'll go ahead and tell you about those now. The hello interval is how often the hellos are actually sent, which is 10 seconds. By default, the dead timer is 4 times that period, which is if OSPF doesn't receive hellos within that interval, it considers a neighbor to be down. So that's going to be 40 seconds, because that's 4 times 10 is 40. And in Cisco especially, if the MTU doesn't match on both of those, the DBDs won't be able to exchange because it sends at that maximum MTU that interface can support. which can be a problem. OSPF info exchange. So hellos are exchanged. They pass them back and forth. All parameters match. You know, those ones we talked about right here. If all of these match, we settle in a two-way state. If neighbors continue, they enter the X start phase. The router with the highest router ID becomes the master. So basically, whichever one has the highest router ID starts the initiation of the DVDs. You know, he sends out my descriptors. If I see some descriptors that I don't have in my route table, like I said earlier, with using the LSRs, I'll request a full version of that. You'll then reply to me with the LSU or the update messages, and I'll acknowledge them. Once all the routes have been exchanged, you know, both of our both of our link state databases are identical. We settle, we're actually considered adjacent at that point, and we'll go ahead and run the SPF algorithm to calculate our best paths to different subnets, and then we'll enter all that information into our route table. OSPF designated router, also known as the DR. It optimizes route flooding on multi-access networks, creates type 2 LSAs, and we'll talk about the LSA types in just a second. DR election takes place after routers become neighbors, but before DVDs are exchanged. Hello messages contain a DR of 0, then you know that one hasn't been actually, a DR hasn't actually been assigned. Actually, you guys can read all this for yourselves. I'm just going to go ahead and explain it really fast. What happens is you have a DR on a broadcast network. Say a broadcast multi-net access like an Ethernet network. So what it does is it gives you a single router that everybody communicates with. So in lieu of just sending your updates blindly to everybody out there, you elect one guy to be the designated router, and then also a BDR, or a backup designated router. So you send your updates to 224.0.0.6, which is the DR. The DR takes those updates and then he sends those out to everybody else. So you have a single point of flooding in the network. So rather than everybody flooding constantly, everybody sends their updates to the DR. The DR will then digest those and then send them back out. You also, your BDR actually also listens to the 006 routing updates. So you know, because since he's the backup, he has to be listening, inheriting those roles. So if the DR does fail, he'll take over as the DR and pick up right where he left off, and then another BDR will be elected. There is no preemption. So if your DR fails, the BDR takes over. Your DR is not actually automatically going to take back over. If he comes up quick enough, he might be able to be elected the BDR if he gets involved in that process. But until the active DR fails, he won't have the opportunity to take back over. You can see here in the election process, higher RID wins. And remember, we can't have matching router IDs, so there won't be a tie there. BDR is also elected. Neighbors send updates to 006. We already talked about that. LSAs will be sent to the DR and BDR. They're implemented to the neighbors. So we pretty much covered all that. OSPF design. You've got ABRs, area border routers, and we'll talk about areas in just a second. And ABR is any router that touches two areas, just more than one area. ASBR, Autonomous System Boundary Router, that's going to be any router that actually injects external routes into the OSPF process. What's an external route? Something you redistribute from BGP, or something you redistribute from RIP, or say you redistribute static, or you redistribute connected. That's actually considered external to your OSPF process, so that makes you an ASBR at that point. Using multiple areas, what's the whole point here? Smaller LSDVs in so your router doesn't have to keep as many link states database as much information as linked state database. Sorry, so many acronyms, I get it all jumbled up. He doesn't have to keep as many routes in his linked state database, so it's smaller. The SPF calculation goes faster because there's fewer entries. It also uses less CPU when it's doing those calculations because there's fewer things to figure out. Failures in remote areas only cause partial recalculation, which is a pretty big one. Depending on the size of your network, if there's a lot of routes in another area, say something goes down, remember we said within an area your linked state databases have to match on all routers. Well, if you have another area, say you have area 0, which is the backbone area, which is required by OSPF, that has to exist somewhere, and all other areas to interconnect to other areas need to touch area 0. If you have a bunch of routes in area 1 and say you have 20 routers in area 1 for some reason, and you lose a route, all of those linked state databases in area 1 have to all reconverge. They all have to become equal so they can run the SPF calculation. And once they do that and that gets complete, the other guys will see that route go away in area 0. That route will disappear, but it'll only do a partial SPF calculation because it's not having to update all of that linked state information. So it's actually less CPU intensive, less memory intensive on your other areas. Routes can only be summarized at area borders, and again that's because we said every router has to have the complete picture. Every LSDB inside of an area is going to be the same, so you can't actually filter anything on a single router or summarize on a single router because his linked state database for that area wouldn't be the same as everybody else's. That's why you can only summarize like going into one area or into the other area. Also, in other areas, the type 1 and 2 LSAs aren't sent into an adjoining area, and we'll talk about that. Type 3 summary LSA is passed. OSPF LSA types. Get a quick drink there. Not used to talking for extended periods of time. Linked state advertisements are OSPF's method of sharing routing information. So type 1 is considered router. One per router, list router ID and all interface IP addresses. So if I've got Ethernet 1 interface in area 0, he's going to create a type 1. He's going to shoot that over to the DR, and it's going to list his router ID and all his interfaces, or rather all his IP addresses on interfaces in that same area. Type 2 is going to be network, and that's created by the DR alone. If you're on a non-broadcast multi-access type of network or something like that where a DR isn't actually elected, which I'm not going to go through because I'm trying to cover what most of you guys are going to see. That would be like a frame relay type of network. Type 2s aren't created if there's no DR. The DR alone creates that, which is just kind of a representation of the subnet and the route interfaces on there. A type 3, the net summary, is created by an ABR and injected into another area. So those type 1 and 2s are suppressed. Excuse me. Type 4 is the ASBR summary advertised a host route to reach an ASBR created by ABRs. So if you actually have a type 5 created in say area 1, whenever it hits the ABR that connects it to area 0, a type 4 is also created, which is a route used to get to the original ASBR. AS external type 5 is created by an ASBR to inject routes into the OSPF process. So that's really anything ejected by an ASBR, anything external when you do your redistribution, from another routing protocol or static or connected, that's going to come in as a type 5. a type 7 is only created in a not so stubby area, and we'll talk about those guys in just a second, because in NSSA type 5s aren't allowed. So in or rather in a stubby area, type 5s aren't allowed, nor are they allowed in a type 7, or rather nor are they allowed in an NSSA. So he'll create a type 7. As soon as it hits the ABR, it'll actually get translated to a type 5 and then sent out to the backbone area or what have you. I know that seems confusing, but hopefully a little bit of that sticks. I'll reiterate those a little bit later. I'll talk about them again. So areas can be expressed either in decimal format, which is really a Cisco thing, or a dotted format. Cisco can do dotted format as well, but the Mikrotiks by default are in the dotted format. Every area must connect with area 0 to reach another non-backbone area. Summarization happens there. Let's see. There you are in the area tab. By default, you got backbone on every router is already sitting there. Area ID 0000 because it's area 0. OSPF area types. Areas have 3 types. You got your standard, your stubby, excuse me, and your not so stubby. Cisco goes on and puts a couple of proprietary extensions onto that, and they add the word totally stubby and totally not so stubby, which seems kind of backwards, but it's actually a pretty interesting implementation. So stubby blocks, or rather stubby and NSA block type 5s from coming into an area. They instead inject the default route. So what does that mean? It means no external routes come in, it just adds a default in. So if you have a little network that's hanging off to the end that's got no other outlets, you can make that guy a stub. And instead of bringing in any routes that are external to the area, it will just send in a default route and say, to get anywhere, really just go through me. Here's a default route. And so it's supposed to lighten your LSDBs, obviously because it's not bringing in those externals, which is going to lower your SPF calculation, all that good stuff. Stubby blocks 5s and allows no ASBRs inside that area because no type 5s can be created, because every ASBR, when it injects a route, creates a type 5, which means that can't happen in a stubby. And the stubby designation has to actually be set on every router that's in that area. NSSA, not so stubby area, blocks 5s inward, but it allows that within that area, it allows type 7s to be created. So an ASBR in NSSA, love all those acronyms, will create type 7s, and whenever they hit the ABR that heads back to the backbone area, we'll go ahead and translate that 7 into a 5 and kick it out so those other guys know how to get to those externals. Let's see here. Let's see, was I in there? Yeah, there's the type. NSA or stub. OSPF path selection. So whenever a router has his LSDB and he's getting ready to run his SPF calculation, he's going to look for the shortest path to area 0. What's the quickest way to get to area 0 for a route? That's what he's going to take first. Then take shortest path across area 0 without jumping through some random area and then swooping back in. Take the shortest path to the destination without traversing area 0 if you can help it. OSPF is really a link state inside the areas and distance vector between areas, and I'll talk about that in just a minute, because it's the idea of you keep the full link state database within an area, but say I'm backbone or say I'm on the backbone area 0, and I've got say that's the hub of a wheel, and I've got several spokes going all the way around, I don't have a complete picture on what those other areas around me look like, so I'm really just kind of doing hop count, to figure out which route to use. I'm just using hop count to get to those other areas. And so OSPF is technically not distance vector, but in between those areas, where he's only got those type 3 summaries, he actually acts like a distance vector. And he also doesn't necessarily use least cost path to area 0. Now, when I say cost, every connection between routers has a cost associated with it, and that's the metric that OSPF really uses to figure out, how to find that shortest route. By default in Mikrotik, every hop is a 10. So if something's 4 hops away, to get to one route, and then I can take an alternate path and it's 2 hops away, if cost is 10 on all those links, well, it'll be 40 to get to one, it'll be 20 to get the other, so I'll take the 20. So it doesn't necessarily use least cost when it's getting to area 0, and I'll talk about that in just a second. It's possible to have equal paths that are different route types: intra-area, inter-area, external type 1 and external type 2. In these cases, cost is ignored, and instead it uses the following area: intra, inter, E1, and then E2. Whenever you inject external routes, you can inject an external type 1 or an external type 2, and I'll talk about those a little bit more in depth later. It really just has to do with the way the cost is calculated on those externals. Okay, so this is OSPF path loop avoidance. It's got some loop avoidance mechanisms inside, which also cause it to not always use the least cost path when going to area 0. So say subnet A right here is advertised, it lives on Mikrotik 1 and it's advertised. See how subnet A is in area 1, and then we've got area 0, which is our backbone area, and then here's area 2. As you can see, if I want to get from area 2 to area 1, I have to traverse area 0, because every area that wants to reach another non-backbone area has to go through the backbone area. And that's the concept of areas, really. Area 0 is kind of the core, the hub, and everybody else just kind of lives around that hub. Oops. There we go. Everybody else lives around that hub off of them. So if you're looking right here, so subnet A is in area 1, so that type 3 is advertised into area 0, then that type 3 is then transferred over to Mikrotik 2 and Mikrotik 3, so they both have that subnet, right? And so if you look at the cost, it's 1 for this Mikrotik. It's 2, the cost is 2 for Mikrotik 3 to get to subnet A. Well, Mikrotik 2, the cost on this link has been set to 50. So it's going to be coming from Mikrotik 1, it's going to be 1, and then once it gets to 2, it's going to be 51, because it adds up those costs as it moves away. So you got a cost of 51 and a cost of 2. If you're looking at the link between these Mikrotik 2 and 3 here, you see they're squarely in area 2. And the cost between those guys is 1. And so if you're looking at Mikrotik 2, what looks like the shortest path to, I mean, what may be the shortest path or best path in your mind would be cost 1, cost 2, and then cost 3. Because if you add them up, that's 1, 2, 3. Whereas here, it's still going to be 51. So it seems like it would be more efficient to go this way. But these part of OSPF is, one, ABR won't advertise another route that was learned from backbone, or rather area 0, the backbone area. So this subnet A won't be, I mean, it'll make it over here to 2, but he won't actually advertise that he knows how to get to, or actually he'll advertise, but 3 will ignore it. So these guys will ignore any routes given to each other that were learned via another non-backbone area. So they'll learn that route in here, area 0. Area 0 will spit it to him. He won't accept any routes that Mikrotik 3 tells him that come through here. What that does is that keeps loops from occurring, but it also will oftentimes make you use the not necessarily the least cost path, because remember, our path selection was always shortest path to area 0, and the shortest path to area 0 is right here because he's directly connected, as opposed to going here and here as well. That's probably clear as mud, but if you read through this and look at the diagram a few times, it'll click. OSPF diagram for a single area. So if we're just going to add, golly, I keep accidentally scrolling. So if we're just going to add every single interface into the OSPF process, we can do that by using the network command. That's generally what that's for. The network command, a lot of people think is in OSPF. They think, how do I get my IP addresses to be advertised into the OSPF process? And they think, oh, well, that's what the network command's for, which is actually untrue. The network command in OSPF designates which interfaces are supposed to participate in the OSPF process. It's really just saying this interface participates in OSPF. Whatever IP address is on that interface is going to get injected into the OSPF process, but that's not necessarily what it's specifically for. It tells OSPF to operate on this interface. So, what I want OSPF to run on Mikrotik 1 is just these inside interfaces, because I don't want OSPF running between me and my service provider. Not that he would have a router up, but I don't want to give him that opportunity. So I'm going to go into networks. I'm going to add an interface, or rather I'm going to add let's see what we got here. What you want to do is you can either do individual host addresses, so I could put the individual host addresses, but what I'm going to do is I'm just going to put in a subnet that will encompass all of the interfaces I'm interested in participating in the OSPF process. So I'll just put in 10.0.0.8, which will cover Ethernet 2, 3, and 10, but will exclude Ethernet 1. So I'll say 10.0.0. 0/8, and I'll have those inject to the backbone area, because remember, by default it's got an area named backbone area that's area 0. So I added that on, and you should be able to come over here to instances, rather interfaces, and see that it dynamically added these guys in. Now, what's this interface menu for? This is so you can do additional configuration on your interfaces, and I'll talk about it a little bit more in just a second. And you can add them manually, or whatever network statements, whatever interfaces get brought into the network statements. If you don't already have an interface configured, it'll dynamically get added if it's covered. So you can see that we got it running on our inside interfaces. So we've got that dude running the OSPF process. Let me go ahead and bring up Mikrotik 2 on the OSPF process right there. Let's see, routing, OSPF, networks, areas. We got our backbone area there. And I'm going to go ahead and inject everything. So I'm just going to do 0000, which I'm generally against. I like being really as specific as possible. Go ahead and put in the specific subnet, but just for the sake of time, I'm going to use 0000/0 just to get it all in there, which by default is what it sets up. So I'm going to come over here to interfaces, and you can see them all dynamically come up. So also on the interface command right here is where you would add authentication if you're doing such a thing. So in our configuration, this is where customers are going to hang off of, right? But say I don't want I don't want any customers having the ability to join my OSPF process, but I wanted that 192.168.2.1 IP address to get injected into OSPF, and I didn't want to do any redistribution. I just wanted it to just to be in with that network command. What I can do is I can set something called passive interface. What's that? Ether 3 right there. So on Mikrotik 2, I'll go ahead, even though it's dynamically there, I can go ahead and add it. No, it was Ether 3. This is also where you set the cost. So if you wanted to manually manipulate the cost on an interface, you could do it here. Priority. Whenever a DR is getting elected, I think I neglected to say this earlier, if you have a priority set to 0, this router won't attempt to become a DR or a BDR. It'll just participate in the process. Higher the priority number wins. This is where you'd set up authentication if you're going to do as such, but that's not what we're doing. This is also where you can set the network type. By default, it's a broadcast because it's Ethernet. You can do point-to-point, non-broadcast, multi-access, point-to-multipoint. And that's where these network types also need to match. Say I'm trying to do a broadcast network to a non-broadcast multi-access. Since those are different network types and DRs aren't elected on non-broadcast multi-access, they'll fail to actually become adjacent. But that's neither here nor there. Passive interface is what I'm interested in. So what this does is, though the network command covers this interface, if I set that as passive, and you can see since I manually added that, it dumped the dynamic entry. If I set that as passive, that IP address that the network statement covered that's on this interface will technically be in the OSPF process, but nobody will be able to form an adjacency to me through this interface. So if a customer plugged into here, and since I wasn't using any authentication, and they just tried to join my area 0, they wouldn't be able to do it because I'm passive interface. I'll neither send nor receive any hello messages out that interface, and nobody can technically join my OSPF area right here. So that's what the passive interface does for you, as well as it's kind of an extra step of protection. You know, you could use authentication, but passive interface doesn't even send any messages at all. And so we've got everything in the OSPF process there, I believe. Yeah. Now we should be able to come over here to routes, LSAs and routes, link state advertisements that we've received. Let's see, 10.0.0.1 is router 1. We're on router 2, so you can see that we've actually received the LSA for his router. And what's router? That's going to be a type 1 LSA. Type 2 LSA. And you look at routes over here, we should see 10.0.0.1 coming from him. That's a legitimate route learned from router 1. You can see the cost associated with that. So now I'm going to go ahead and make sure I've got OSPF running on these other guys. And I had most of these guys kind of pre-configured just to save a little time. I just had them disabled. I'm just adding everything there. You can see my interface is coming up. Let's see. Router 2. Let's see here. Let's see if he's doing it. You can see that he auto-configured himself to 10.0.0.2 as his IP address because that's the lowest. But router 2, I don't want him to have that ability to even guess. I'm going to go ahead and set his router ID to 10.0.0.2. We kicked on router 3, and I think I need to enable router 4 real quick. Routing OSPF. And there's the backbone area. I believe 5 and 6 are already up. So let me see. Router 1. Let's check out our LSAs. Sort by type. 1, 2, 3, 4, 5, and 6. We've got them all there. got our routes that we've learned from all the different guys. Here's the gateway. Look, you can see a couple of equal cost routes there, and that's coming off of router 4. You can see so Mikrotik 1 is what we're looking at. We have equal cost routes to this guy because all the links are set to default, so it's cost of 10, 10, 10. If you look, you see the cost is 40 to these subnets over here. Let's see if we see anything interesting in here. Intra area, which means they're all in the same area. See all the associated costs, interface to reach those. Let's see if we have anything more interesting. Network, that's going to be type 2 LSA right there. Let's see if we've got anything interesting. Let's go into OSPF here on Mikrotik 1. Now, we need to inject a default route because he is our internet router right here. He's our border, and so we want all these guys to know to get to the internet, just use this default route. So we'll inject the default route via the instance in here. Redistribute default route. You've got 4 options. Always as type 1 or 2, or if installed as type 1 or 2. What does that mean? Always means installed means if you've already got a default route in the routing table, then go ahead and redistribute it. If it's not there, then don't redistribute. Always means whether there's the default route already in the routing table or not, go ahead and redistribute it. Now, what does type 1 and type 2 mean? That means external type 1 or external type 2. Remember, external type 1, in the case of equal cost paths learned via different types, external type 1 takes precedence over external type 2. External type 1, what it does is it takes the ASBR's cost to get to that route, and it adds up every cost along the chain. So if we do always as type 1, we apply that. What that means is it's going to take default of 1, and over here it's going to add 10 to it, so that'd be 11, and then it'll add another 10, so that'd be 21. So it's always going to add those costs away from the ASBR. So let's go to 4, which is at the opposite end of the chain, and let's look at the route. There's our default route. You can see it's coming up as external type 1, and it's got 31 because it had 3 hops away, plus the 1 is the route learned from the ASBR. Now, let's change it to external type 2. What does that mean? External type 2 only uses the cost that the ASBR knows to get to that route. So if the cost for that ASBR is 40 just on that ASBR, let me jump back to our diagram. So if the cost for him to get default is 40, then this guy will see it as 40. If the cost for this guy to get to that default is 1, then this guy will see it as 1. It doesn't take into account the cost down the chain. It only wants to know what's the cost for the ASBR. What's the ASBR reporting that cost as? It doesn't care about the cost to and from. So type 1 cares about the ASBR's cost to get to that route plus every subsequent route to get to him, so it'll add them all up. Type 2 only cares about this guy's cost. Doesn't care about how to get between the two. Now, you'll notice, even though I told you that type 2 shouldn't care about the cost all the way to and from, it's still reporting 30 and it's not showing the 1. That's because there's a bug in 4.5, 4.6 with the OSPF implementation, which after I reported the bug, they were nice enough to be able to reproduce it and told me that it's going to be fixed for 4.7. So you guys probably, by the time you read this or see this video, 4.7 will either be out or be close to being out, or it'll come out so long ago that you'll laugh that I'm even talking about it. But it should be fixed soon if it hasn't been fixed already. So technically this should be reported as a 1. on this 4, even though it's actually being reported as a 30. You can see what they did is they accidentally reported the cost to the ASBR and subtracted the ASBR's cost, as opposed to subtracting the cost to the ASBR and just showing it. So they did it kind of backwards. Just for your information, version 3.30, I tested that not too long ago with this, and it actually works correctly. It's just the SPF calculation on 4.x right now. Up to 4.6, it's supposed to be fixed in 4.7. So that's injecting the external route right there. So now, as it stands, from Mikrotik 1, I should be able to reach any of these guys' networks. And they're all in the same area right now. So in theory, I should be able to ping 192.168.4.1. So if I jump on 1, go ahead and close that. IP routes, go ahead and show you the route table. 192.168.4.0/24. It's equal cost paths right there. So I'm going to go to Tools Ping. 4.1 is still in there, super. And you can see that it goes and it knows how to return as well. And that's actually just configuring those guys. Now we'll talk about OSPF multiple areas. This is where you try and add a little efficiency in. If you're if you're a large network, and say over here in this area you had several routers that hop through, say you have a big man, over here, and you hop it through several other routers and run OSPF. That'd be a good use for an area there. And say it's a similar situation over here. You've got a large distribution over here, and then you've got some customers that bring routes up and down somewhat infrequently or maybe frequently, and you don't want this other area to do an SPF calculation all the time. That would be a good use for another area. Say you're a WISP and you're doing PPPoE, and you're assigning public IP addresses via PPPoE, user manager, what have you, on these interfaces. What I would do is on your PPPoE server, to get that /32 public address that you're assigning to somebody off this sector antenna right here, you can set up a network statement that will encompass that public subnet that could theoretically exist there. Excuse me. And then you can have it injected into area 4. So whenever that guy comes up, this guy right here, whenever he comes up, he'll jump into that area 4 over here. That'll get sent out as a type 3 LSA into your network. If that guy flaps back down, you know what? Everybody else doesn't have to do a whole reconvergence in here. They don't have to do an enormous SPF calculation. They'll just do a partial calc. So these guys won't see him flapping up and down all the time. That's another good use for multiple areas. So I'm going to go ahead and turn on my secondary area for 6 and 4, because they should be pre-configured, and then I'll manually do it on Mikrotik 2 over there so you can see that. OSPF. Let's see. Areas. Kick that guy on. Area 4 for Mikrotik 4 networks. So Mikrotik 4, you see here, it's got 3 interfaces, a 10 dot, a 10 dot. The bridge interface is 10 dot, and the Ethernet's over here 192. And I want area 4 to be the 192 stuff. So I said anything on the router can be backbone, and then I have a more specific here for 192. So it's going to check, see that more specific first, and take it. I got my area actually up. Alright, you see area 3 is in area 4, or rather, interface 3 is in area 4. I jump on my 6, kick him on, rather routing, OSPF. Oops, area 6 for router 6, that guy cut on. Ether 3 is in area 6. And then Mikrotik 2, as per the diagram right here. So 192.168 needs to be in area 2. So area, and I'll go create area, I'll name it 2, and then I'll put it as 00002. And then network, I'll add the network in there. 68, and I can do 00, or I could be specific and say 2.0/24. I'm going to change it so that it'll be in area 2. That's all it takes to create an area. Interfaces, there you go, area 2. So let's check out our LSAs and see if we got anything in there yet. We've got our external, because that's being injected from Mikrotik 1. Network, which is going to be type 2s coming from the backbone area. Area 2, here's a router ID. That's our router ID from area 2. Let me sort these by actual area first. And so you can see in the backbone network, we've also got some summaries right here. And remember what summaries are. The summaries are the type 5s that are sent to us from other areas, or rather they're type 3s that are sent to us from other areas. So remember, it suppresses the 1 and 2 and just sends us a type 3 into alternate areas. And then if we scroll up to the top for area 2, you can see that we have one router LSA, which is our type 1. And then here's a bunch of type 3s that came from our backbone area, area 0. Excuse me. So let's go ahead and take a look at say area 1's table, just to see what he looks like. So we've got, since he's only a member of one area, you see backbone here. Network is type 2, routers type 1, and here's our type 3s from the other areas. And they're still just as reachable. And you can see their originator ID right there. Here's the routes. And you should see enter area for that LSA type right there. See, enter area because they aren't in our area, and enter area because they are. There you go. So that's multiple areas, really easy to configure. Full duplex links via OSPF. This is people doing wireless. In Mikrotik, you can do the dual end stream, which is the proprietary extension on 802.11. Dual end stream means you have two cards. You configured one to be send and the other one to be receive, and on the far side you run dual end stream over there, and you have the opposite one running send and the other one running receive. So what happens in dual end stream, if you drop a wireless card on one of the sides, your wireless link between the sites completely fails, because one's designated as send and one's receive, and it can never violate that. It can never all of a sudden decide to send and receive. So an advantage to using OSPF is you can manipulate costs to make a router or rather a side only send and then the opposite side only receive, just via the cost in OSPF, because it'll get established in the route table as such. So if you look here in this example, this top one, using, say this was an RB750, and then you had a ubiquity radio here and a ubiquity radio here. Same thing on this side, 750 with a ubiquity and a ubiquity. You can do it just the same as if it was actually, say this is a 52H and this is a 52H, and they're inside the Mikrotik. You know, say up here these are bullets, so these are just Ethernet interfaces going to those bullets, and here these are actual wireless cards in the routers themselves. It works the same. What you do is you create that interface. OSPF, you go to the interface tab right there, and so for right here in this interface, 10 is our default cost, so we're going to set a lower cost on Ether 3. You would say Ether 3 cost is 1, right? So what that's going to do is it's going to say in this route table, I've got a route, I've got 2 routes to the same location, because once OSPF comes up, he'll know that he can reach this router via this one and via this one. It's this equal distance, but this one's got a lower cost. So I'm going to install this route right here to be the best path to get to Mikrotik 3. So all traffic will send only this way. And it'll be the opposite over here on Mikrotik 3. It'll have a lower cost here. So I'll say Mikrotik 1, I've got a lower cost to go out this path, so I'm going to send here. So in effect, you only send this way, and as far as Mikrotik 1 is considered, you only receive this way. And as far as 3 is considered, you send this way and you receive this way. So in effect, we've created a full duplex link. It only sends that way, and this guy only sends this way. Now what happens if this radio dies, or down here in this example, if this radio card dies? This will automatically fail the link. The OSPF will lose this entry out of its LSDB. It'll rerun the SPF calculation, and it'll see that there's only one route left. So it'll go ahead and send and receive on this link. Wireless being a half duplex medium, if you can tell it to only send, you'll get a lot better throughput, but I would much prefer this link kicking down to half duplex than not working at all. So OSPF actually affords you a nice little full duplex option there. Alright, moving on to BGP. So the other one was an IGP, and this is an EGP, external protocol. What is BGP? BGP is the routing protocol that the internet runs on. Is it something you're going to necessarily run inside your organization? Probably not. At the data center, we run BGP because we hold the full internet route table on all of our backbones in our data center gates. So most of our equipment actually holds the full internet route table. We've got some pretty beefy equipment there. Are you technically going to need that? Most likely not. Where are you usually going to use it? At your border. When is it typically used? When you have multiple providers. And why do you use BGP? Well, on the internet, a lot of routing happens asymmetrically, as in it can send on one link, it can go down one link and return on the other. I'll use this as an example. If this were the internet, my traffic wouldn't necessarily go this way and then come back this way. My internet may go this way and then return this way. You know, there could be 40, 50, 60 other nodes in here in a big spiderweb fashion that I could return on. You never know which path I'm going to take. If something fails, it automatically will reroute and come back to me. Thus, the power of the internet is that it's so reliable. Any one part can fail. So if this is my ISP right here, and here's my two internet providers, I've got public address space from Aaron here in the States. Say I've got 1.1.1.0/24 is my subnet that Aaron assigned me, and I advertise that to both providers. Provider 1 fails, that addressing publicly available, publicly routable rather, is still going to be available via here. You know, I can have these links symmetrically routing. This one fails. This one will pick up the slack via BGP. And that's how most providers are going to want to hit you if you're multi-homed. So having said that, I'm going to keep this short on a suggestion of a buddy of mine named Brian. He said that most guys in the Mikrotik world aren't going to be doing BGP, so you might keep that a little light just to keep people from going to sleep. So I'm going to do that. I'm just going to kind of give you the quick and dirty and give you a quick example of how it works and some of the initial things you're going to want to configure to bring up an internet connection. I'm also going to go a little bit further and do some internal BGP work, but at that point you can just zone out and not pay attention if you're never going to get there in your infrastructure. Uses path attributes instead of metrics. The most commonly used one is AS path. What's AS stand for? That stands for autonomous system. Autonomous systems are like a cloud of addressing that may live in there. And so when yeah, here it is, path vector logic. So it doesn't do like hop counts. So instead of thinking router to router, it thinks autonomous system to autonomous system or path to path. That's how it actually works. Instead of logically, when it looks at its table, it's thinking, you know, which autonomous system cloud do I move to next? So it thinks big picture. You know, it's like say if the post office, you know, BGP's thinking, which city do I need to send this letter to? You know, do I need to send it to Bryan or College Station? You know, and so it'll send it to College Station. Well, then your IGP, once you get inside your ISP, say I'm the ISP for College Station, you know, I'm the post office in College Station. Say I'm running OSPF inside. Well, then OSPF is going to say, you know, which street inside of College Station. So then OSPF will deliver it to that router that runs that street, and then that router will say which house, you know, which is going to be which specific IP address in that subnet that I have do I deliver it to, you know, which will then make it to the MAC address, which is the mailbox. So BGP is very much big picture. It looks for autonomous system hops. It uses TCP port 179, which is a big nod to TCP, how reliable it is, because TCP is what BGP runs on. I mean, TCP is what makes BGP work, and BGP runs the internet, so it's got to be a pretty reliable protocol, huh? Default keep alive timer is 60 seconds. If it doesn't see a message for 3 times that keep alive timer, it's considered the other guy dead. IBGP neighbor is an internal neighbor, which is just another BGP peer that's got the same autonomous system number as you do. EBGP rather, is external, and that's going to be another peer. It's going to be a peer that's got a different AS number than you. So all of your routers in your infrastructure are going to share the same AS number. There's a caveat to that. There usually is. It's called confederations, but unless you're really big, you're not going to use them, and it's way beyond the scope of this. Even though Mikrotik does support, I believe, confederations. EBGP is technically what most of, or is probably what most of you guys are going to be using, or probably the only thing you guys are going to be using if you're doing BGP at all, and that's what you're going to peer with your ISPs with, your upstream providers. So internal neighbors, part of the same system, part of the same AS. By default, routes learned via your IBGP neighbors. The distance is 200, higher than that of EBGP, which is 20. It's also higher than that of static. So if you have static routes that are more specific than your BGP routes, those will get used. IBGP neighbors generally peer via loopback, because IBGP is usually going to have kind of a big mesh, and it could even have multiple connections between 2 of the same devices. So if you have 2 connections between 2 routers and one of those connections breaks, what it allows you to do two connections between two routers, you only have to do one peer statement if you do it to the loopback address. So it doesn't matter how it actually gets there, which interfaces fail, which are up, it doesn't care, because it's peered via loopback. It'll just reroute through those other existing interfaces. That's why generally people do that. IBGP is generally assumed to be fully meshed, which can be confusing for some people, and it was for me at first when I excuse me, was first learning about BGP. What does that mean? It doesn't mean that your internal network looks like a spider where every router physically plugs into every other router. You don't actually have to have that. You just have to have peers between those routers. So say you have an IBGP infrastructure, and there's all of your routers are in a line, and you've got 4 routers in a line. Router 1 technically needs to be IBGP peered, needs to have a peer statement with 4, because BGP neighbor 2 and 3 in between assume that since you're IBGP, you have a full mesh, so you're already peered, so you're learning your routes that BGP neighbor 1 is teaching. You're learning those directly from him. So don't have to be, IBGP doesn't technically have to be completely cabled every single router to every single router, but you need that peer statement in for every single router to every single router. There is a caveat to this too. It's called route reflection, and we'll talk about that in a little bit, which can actually be pretty useful for stub routers inside the IBGP infrastructure. By default, IBGP routes learn to keep the advertiser's next hop attribute intact, which can be overridden with the next hop self is what it's called in Cisco, or self I believe is what it's called in Mikrotik's implementation. Let's go ahead and take a peek. Routing, BGP. Let's see. It's going to be under the peer. Next hop choice right here is what I'm talking about. Overriding force self. That's what it would be. And IBGP only advertises what's considered to be best path to its other peers. So if you've got say 2 ISP providers, and they're teaching you, they're giving you equal, they're offering you 2 routes to the same network, you're going to figure out which one's best path as far as you're concerned, and that's what you're going to advertise to your IBGP neighbors. You're only going to tell them what's considered to be the best path. You don't give them every single route you have to that same network. You're going to figure out which one's best, and that's what you're going to tell everybody else about. Flip side of the coin, eBGP, these are going to be your external neighbors. This is going to be your internet provider or upstream providers. Administrative distance for these learned routes is technically 20, which is lower than IBGP. We talked about that earlier. Neighbors generally peer via the connecting interfaces IP addresses. Caveat to that would be your upstream provider, you have 2 physically cabled connections to him. You might peer via loopback, so that connection will appear to always be up. Routing will kind of do its thing. External neighbors are assumed to be directly connected, so the TTL is set to 255, which means you have to be directly connected. You can change that behavior in the peer statement as well. Where are you at? Is it in the advanced? No. Should be multi-hop in here. Multi-hop, there you are. Golly, staring me right in the face. Hit the multi-hop. Which means you're multiple hops away. End of a long day, people. Let's see. EGB routes. assume the next hop, so it does kind of the next hop self or force next hop self. You can override that again with the hop propagation option I showed you earlier. Care should be taken with EGP neighbors to prevent yourself from becoming a transit point. You've got multiple providers. If you're pulling the full internet route table from 2 internet providers and you're giving them the full internet route table back, you're sending it back to them, you might look like a better hop to that other provider than their directly connected link some other way. You know, maybe they're linked to that provider's 2 hops away or 3 hops away, and you're only 1 hop away. You know, you're 2 hops away even. The other guy's 3 hops away. Well, you're going to look like a better hop to him, so he might start using you as a transit point. So what you want to do is, to your neighbors, you only want to advertise out to your upstream internet peers the subnets that you technically want them to have. So your errand given IP address space is what you advertise out to your neighbors, and that alone. That way you don't become a transit point and consume all of your internet connection, and your internet bills go through the roof because you were looping and swooping some traffic for your provider. Building the route table via BGP. We talked about the administration distance already. BGP next hop. So when you get next hop information, well, when you get NLRI, network layer reachability information from your neighbors, whatever they have set as the next hop for that route actually has to be reachable via your local route table. That's why you have to run an IGP like OSPF so that you know how to get to that. And generally with OSPF, if you're in your IBGP infrastructure, if you're running the full internet route table, you'll only put into your OSPF process your directly connected links, and you'll let BGP take care of the large-scale routing. Routes can be added via the network command or via redistribution. Addresses can be summarized via aggregation. So, network commands. In BGP, if you want to actually inject something into the BGP process to be advertised out, you do that with a network statement. It's not like OSPF where you're adding interfaces into the process. Networks is how you actually can introduce some stuff. If you don't want to redistribute, you can use a network command to pump it in there. Aggregate, if you want to do some CIDR notation on some of your addressing to advertise out to peers, you can do that via the aggregate command. I believe you can add this in here and say if it's a large sweeping subnet like that, you can say summary only, so it'll suppress all of those smaller 10 dots that fall underneath that guy. So it can make your routes look more efficient. And the network command being, you can put any network in here that you want. Synchronized means it has to exist in your routing table. Unsynchronized, without the checkbox, means it doesn't care whether it's in your routing table or not. It's going to advertise it as if it exists within your infrastructure. So that can be a little dangerous. Cisco, on the other hand, if you want to advertise something out via BGP, it actually has to be in your route table in one way or the other. Route reflection. I said we were going to talk about that earlier. If you have a stub BGP router in your IBGP infrastructure, you know he's got no exit point except for one upstream router. What you can do is called route reflection. And I'll use this example right here. So this would be the route reflector server, and this is going to be the route reflector client. So remember, by default, all IBGP is considered to be fully meshed, except for a single situation called route reflection. So if this guy's the client, this guy's the server, what he'll do is any other IBGP routes he learned from any of these other IBGP neighbors, he'll send those over here, which technically OSPF doesn't do. But since this guy's route reflector mode, he'll do that. So this guy doesn't actually have to be fully meshed. He only has to be peered with this guy because he's going to route reflect everything over to him. Now everything this guy as the client teaches him, he'll go ahead and advertise out to all of his fully meshed peers. These three routers, since they're IBGP, are all going to be fully meshed. There's two pure statements in here. Rather, there's going to be three pure statements in here. One for him, one for him, and one for him. Mikrotik 2 is going to have only two pure statements in here. One for this guy and one for this guy. Why isn't he fully meshed with this IBGP neighbor? Because this guy's acting as a route reflector client. It's not necessary. He's going to go ahead and teach all the Mikrotik 2 learned routes. Mikrotik 3 will go ahead and reflect those over here. This guy, anything he learns, he'll go ahead and send that up here, and he'll reflect those client updates back out to these guys. Does this guy even know he's a route reflector client? No, he has no clue. The route reflector option's set right here. And you put it on the peer statement and say, hey, this peer's a route reflector client. This guy has no clue. He operates normally. So let's see. Blah, blah, blah. Yeah, that's pretty much it. So here's our BGP example. I'm going to try and wrap this up quick because this has been a long video. And there's so much to BGP. There's so much granularity you can put into it, but I'm just kind of barely scratching the surface of this guy here. It's really just going to be kind of your generic, typical configuration. Some of this is non-typical, you know, the route reflector stuff. And I'm going to show you a little bit of filtering just because I can't leave you unarmed completely. So let's jump right in. I've reconfigured the network a little bit. Excuse me. And what are we going to be doing? I'm going to be, this guy right here is going to be my upstream provider. This is my Quest, my Sprint, my Time Warner Telecom, my AboveNet, my Comcast, whoever you happen to be peering with, your AT&T, anybody. And I'm going to be sending the full internet route table this way. But really the only routes I have in this guy is going to be 8.8.8.0 is really the only thing I'm going to be sending. But in theory, I'm sending him the full internet route table. Now this guy, since this is my wireless ISP or my regular ISP right here, I'm peering BGP via BGP. I'm sorry. The only address space I really publicly own is 2.2.2.0/24, so that's all I'm going to be sending him. Remember, if I eventually bring on another peer, I don't want to become a transit point where I send him the full internet route table and I send him the full internet route table, and gee, that sure looks like a good route to get over there. I don't want to do that. I'm not going to become a transit point for somebody. So I only say 2.2.2.0/24 lives here. That's all I send out. And let's see. So we'll go ahead and take a peek at Mikrotik 6. Let's get him going. Let's go ahead and disable all that OSPF off of Mikrotik 6 because he's not on the end of that loop anymore. Now he's our ISP peer. So routing BGP. Our AS number is 1 for this guy right here. I accidentally have it looping in over here, but Mikrotik 1 actually isn't in AS1. He's just peered with AS1 right there. So, since 6 is AS1, I'll set him to 1. Let's see here. Let me look at my route table, see if did I add a static for that? No, I didn't. So I'm going to go to routing, BGP. Like I said, I'm sending the full internet route table, but really all I'm going to do is I'm going to add .8.8.0/24 in here. I'm going to say don't bother synchronizing. And then I'm going to add my peer. So I'm going to go ahead and add the peer address. I'm going to call this one MTK1. Remember, I'm an ISP instance. I'll leave it default. Remote address is 1.1.1.1 because I'm peering with the directly connected Ethernet interface, because that's generally what you do on eBGP neighbors. Let's see, remote AS is 2. That's what their autonomous system is going to be. Everything else should be good default. So let me go over to Mikrotik 1, and I'm going to say instance, we are autonomous system number 2, and peers, MTK6. That's my internet provider. I'm pairing with him via 2. His IP address, his remote AS is 1. So this is where I'm really telling you, hey, he's external, because I'm saying he's in a different AS than me. Also on 6, let me make sure that I got that IP address on there. Yeah. So let me disable that one and enable that IP address. Otherwise our BGP pairing is not really going to work, is it? There you go. Saw the neighbors come up. So we haven't done any filtering yet, nor have I done any advertising. I'm going to go ahead and advertise 2.2.0/24. You know what? I'm going to do it in a different way. I'll show you a different way to do it, which I think I did in my example. I'm going to create a static IP routes, and I did. I created a static to 2.2.2.0/24 because that's my address and it lives here. I'm going to say it's black hole. What does that mean? It's gonna take anything that matches that and throw it in the bitbug. It's gonna throw it in the trash. Why do we do that? Because it's generally going to be accepted that if we're using this IP space inside our infrastructure, we're going to have a more specific route to it, right? And so if we have a more specific route, this more generalized route won't get used. It'll take the more specific. Say I'm doing PPPoE and I'm handing out /32s. You know, OSPF's going to get that /32. It's going to propagate throughout the infrastructure. Mikrotik 1's going to see it. So this PPPoE client hanging off of this router right here comes up, gets injected into OSPF. OSPF carries that guy over here. Well, then in this Mikrotik 1 route table, it's going to see that more specific, so it'll go ahead and take it. And so if anybody tries to say, somebody on the internet tries to I don't know, just start scanning my subnet or denial of servicing my my address space, and they send it to an address that doesn't actually exist, that black hole route is actually going to catch it and throw it in the trash right there. It never actually goes anywhere into my infrastructure, so it just dies right there. So since we have that route, Mikrotik 1 routing BGP, I'm going to go into the instance and redistribute static routing. So that static route we added should start being, so you come over to advertisements, you can see what's being advertised. You can see that 2.2.2.0 is now being advertised, which is exactly what we wanted. Excuse me. So IP routes, let me check my routing table again. You can see that from my neighbor over there, my internet service provider, I'm getting the full internet route table, even though I'm really only getting 8.8.8.0/24. You can see that came from BGP. That's what the B signifies. And then if we go over here to 6, which is our ISP, you can see his advertisements. He's advertising 8.8.8.8 IP routes. You can see my 2.2.2 coming from my border router, my Mikrotik 1. So now I want to put in my my filtering. Oh, just to show the filtering in use, let's add another static route to 7.7.7 0/24. We'll black hole that guy too. So if we go to our BGP, so that's our OSPF, we should be advertising that out, 777. He should be accepting it, see he does. But technically we don't want to advertise that. So how do we filter that out? We create a routing filter. So I'm going to create the filter, and chain is something meaningful to you. I'll say Mikrotik 1 over to Mikrotik 6. So it's going that direction. Prefix, what do I want to be able to advertise out? I want to be able to advertise out 2.2.2.0/24. That's what I want going out. Action, I'm going to say accept. Okay, and this builds just like a firewall access list. So it's the order is actually important. So I'm going to say Mikrotik 1 to Mikrotik 6. This is going to be our next link in the chain. 0/0 prefix length 0 to 32. 0 to 32. So what does this prefix thing mean? What it does is you define a subnet up here, and then you define, if you don't define a prefix length, this means match this subnet exactly. You know, that precisely. This right here, prefix length, means a prefix, or rather a subnet inside that subnet that may be smaller, that has, you know, a /5 or /6 or a /11. You know, it'll match those as well. It'll match subsets of this subnet right here that have these prefix links after. So a / whatever. So say I did 10.0.0.0/8, and I did / I don't know, 16 to 32. So that would match like 10.0.0.0/16, or you know, 10.0.1.00/16. It would match that, or something /17 or 18 or 19, all the way up to 32. So it gives you the ability to define smaller subnets. So what I'm saying for this is 0000/0, which is any, and any prefix length. So any address, any prefix length, action, dump it, discard it. Okay, so I got my filter set, and an order of operations is important. So it hits the first one. It's going to say accept the route 2.2.2.0/24. If it matches that, it's good. We'll allow that through. If it matches anything else, discard it. And this is exactly what we want to do. We only want to advertise this, nothing more. So now that we've got the filter created, we're going to assign it to that peer going to our ISP, and it's going to be our outgoing filter. You should be able to hit the drop down and see it. Mikrotik 1 to Mikrotik 6. So let's see. Right now, in our route table, we've got the two advertised subnets, 222/24. This is in Mikrotik 6. This is our upstream, and the 777. Remember, we don't want this 777 to be in there, so we're filtering it out. We're saying only the 2s, none of the 7s. We hit apply on that filter that we added going outbound, and you see that the 7s disappeared. We're now filtering out anything but the 222. Route filtering at work. And another good use for route filtering is, say you've got an x86 PC with like a 2.6 gigahertz P4 or something like that, and you just brought up a new ISP peer, and your router's running kind of heavy. You know, it's running kind of lethargic. You know, it's taking a long time for that new peer to come up, and occasionally that peer, say that peer flaps once a month, and it'll take 20 minutes to rebuild the route table for that peer. What you can do is you can filter out incoming routes that are smaller than I don't know, filter out something that's smaller than a /20 to /32. So you can say 0000/0, and then 20 to 32 is the prefix length. So what that'll actually do is that'll cut down the number of routes that are in your route table, which means you'll you'll bring up that that BGP peer faster. You know, your routes will come in and stabilize quicker. There'll be less memory utilization on the router itself. CPU ultimately will go down because of it. So that's another good use for it. Now that we've finished our outgoing BGP configuration, we need to work on our internal BGP configuration. So on Mikrotik 1, remember IBGP needs to be fully meshed, which means I have to add a peer statement for 2 and 3. Peer, we're not going to peer with 4 directly because he's a route reflector client. See, it says right there with 3. So I'm going to go ahead and add the peer to 2. So we're done with 6. So we're going to go to 1. We're going to add a peer. And we'll call it MTK2 because that's where he's going to. Now that we're IBGP, I'm going to peer via the loopback interfaces. So 10.0.2, which is great because it's super easy to remember. Remote AS is 2. Even though I'm saying remote AS, it's the same autonomous system number I have, and that's fine. That's just signifying that he's IBGP. Now advanced, I'm going to say update source, and my update's going to be coming from 10.0.0.1. Now in these peer statements, if you're not peering with that directly connected interface, you've got to tell it what address you do want to peer with, because by default it's going to use a directly connected interface IP as the peer. So if I'm using something alternate, internally I'm using loopbacks, so I'm going to actually specify those loopback IPs as my update source. So looking at Mikrotik 1, my loopback is 10.0.0.1, so I'm going to specify that as the update source, and I'm going to point over to his loopback, and he's going to do the opposite. So it doesn't matter if my peering, if I've got a bunch of routers that connect over here, it doesn't matter if my peering goes this way and loops back in. As long as I'm going to that loopback address, it's always going to end up in the same place and leave from the, theoretically it's coming and going from that loopback interface, so it doesn't really care what interface it goes out of. So back here on Mikrotik 1, we're sourced from our loopback going to his loopback. Okay. And internally we're not doing any filtering, we're just letting it rock and roll. So Mikrotik 2, or rather, let's finish off 1 real quick. I'd add that I'm going to cheat and open up my Mikrotik 2 peer, copy them. Update source is staying the same. My destination is going to 3. Now you see how easy it is to remember what routers are what whenever you assign a loopback. That's easy to remember. If you're doing 10.0.0.1, 2, 3, 4, 5, well, router 1 is 1, router 2 is 2. Makes it super easy to remember. So we've got our peers done for let's see, 6, peer 1, actually let me name that to MTK3. Don't let me forget to do that. Alright, moving on to Mikrotik 2. Let's see. Routing BGP. Alright, we go into that instance, we set our AS number. Okay. Go into our peers. We're going to peer with MTK1. His IP address is 10.0.0.1. That's his loopback address. Remote AS 2, same as our AS number. Update source 10.0.0.2 because we're on Mikrotik 2. Super easy. And you should see that peer come up. And there he goes. Router ID. I would suggest go ahead and setting up these router IDs as well manually. 0.0.2 for that guy. I forgot to set router 1 under the instance 10.0.0.1 because I like to see that in the updates. I like it to match. I like everything to be symmetrical. It makes it so much easier. Alright, let's add our peers in there. Because you can see the remote ID is coming up as the remote address. in lieu of doing that, let's open up this guy, just copy him, and all we have to change is the remote address and the name, Mikrotik 3. Now let's check out Mikrotik 3 instance. That's OSPF. Let's close you. Running BGP. Let's go ahead and set his router ID 10.0.0.3. Mikrotik 3. Already had his AS set. Let's see. Peers. What do you know? Already got those guys in here, configured and ready to go. And bring those up. You can see my peer with 1 coming up. And remember, this is 3. This is router 3, and I'm peered with router 1 via the loopback address. And remember, I'm not physically cabled to him. IBGP fully meshed. You can see our peer with 1 and 2 came up successfully. Mikrotik 4. Let's log into him and take a look. Don't care about OSPF. Routing BGP 10.0.0.4. Already had our AS number in there. Here's our peer with 3. Go ahead and bring that dude up. You should see that established. There we go. So I'm going to go ahead and go back to Mikrotik 3, since Mikrotik 3 is where you actually do the route reflector configuration for 4. I'm going to come into 3, and so 1, 2, and 4. Here's our number 4 peer. So how do we make him a route reflector client? You just check route reflect, and that route reflects over to him. That's all it takes. Mikrotik 4 is completely unaware that he is a route reflector client. You just add that little checkbox, and then you can violate the fully meshed for that that 4th peer down there. So let's look at our route table. I think it's right there. There he is. And so via BGP, you see from peer 1 we're learning 777. From our external peer, we're learning 2222. And our external peer, we're learning 8888. Or actually, that's our border router, and that's our external peer right there. Oy. So we should be able to see those from 4. Yep, same routes. So we're not fully meshed with peer 1 or 2, and yet we're still getting their updates from peers 1 and 2 right there. So thus route reflector client actually works. Now let's take a look at this so you can see the different route types. And where's 1? There's 1. Where's our route table? So that's the route we learned from our eBGP peer. Notice anything interesting from him? Distance right there. Distance is 20, because remember anything we learned from eBGP starts out with an administrative distance of 20. Now jump back 1 leg to Mikrotik 2, and that same route 8.8.8.8, since it was learned from an IBGP peer, now it's 200. So you can see that administrative distance is actually in action. You can see him working there. So we talked about our update source. And here's some references. It's the same reference page I always have on there. Cacti Easy from my great friend Jimmy. It's a terrific product. I recommend it for anybody who does a multitude of devices, you know, from server, network, physical controls. I monitor generators. I monitor switch gear with this thing. I monitor fuel level, all that good stuff. I am a consultant. I am listed on the Mikrotik consultants page. Um, I do work in infrastructure, troubleshooting, all that good stuff. But I also am big about education. I'm turnkey, as you can tell from all these videos. So not only do I want to get your infrastructure up and running right, but I want to teach you how to do it and how I did it and how to troubleshoot it in the future yourself. If you guys have any questions or comments on this, I know I covered a lot of material, and at the end of these long days when I try and make these videos, it always seems that I get tongue-tied and kind of jumbled up, and I'm sure I misspoke about something here or there. For that, I apologize, and ask as many questions as you like. I'll be very happy to answer them, and I'll be sure to answer them as the best of my ability and as expediently as possible. That's not always right away, but as quick as I can. And thanks, guys.